Hello students, myself XII-Sci Gorane, रयत शिक्षण संस्थाज RBNB College, Srirampur. Today we are going to study wave optics, article dependence of wavelength on refractive index of the medium. Firstly, we draw the figure. Suppose this PQ is the refracting surface, PQ. It separates two media. Medium above it is medium 1. Suppose velocity of light in this medium is V1 and wavelength in this medium is lambda 1. Medium below it is medium 2. Velocity is V2 in this medium and wavelength of light in this medium is lambda 2. The plane wavefronts of light are incident here. Plane wavefronts are, suppose light is incident here normally, light is incident normally, and suppose these are the plane wavefronts incident on this PQ normally, and these wavefronts are parallel to each other. Suppose this is AB, wavefront AB, then wavefront CD and wavefront EF. Here light is incident normally, so it travels without any deviation. AB is the PQ is our refracting surface. Light is traveling without any deviation if it travel incident normally on the refracting surface PQ. This is for the normal incidence. It travels without any deviation like this. These incident plane wavefronts, after refraction, this AB is here, that is A dash B dash. It is refracted as A dash B dash. CD is refracted as C dash D dash. C dash D dash. C dash D dash, and EF is refracted as E dash F dash. This is refracted as E dash F dash. As velocity of light in rarer medium, medium 1 is rarer medium, medium 2 is denser medium. These are the plane wavefronts AB, CD, EF, incident plane wavefront. A dash, B dash, C dash, D dash, E dash, F dash are the refracted plane wavefront. As medium 1 is rarer, the speed of light V1 in this medium is greater than medium 2 because medium 2 is denser medium, V1 is greater than V2. So light covers less distance in medium 2 in the same time because speed of light is less in this medium, so in the same time it covers a less distance in medium 2 as compared to medium 1. and suppose the distance between the wavefronts is equal to the wavelength of light, lambda 1 here suppose. Distance between these two wavefronts is suppose lambda 2, and here also distance between the wavefronts is suppose wavelength of the light, lambda 2. We know wavefront covers a distance lambda 1 in periodic time t. In periodic time capital T, the distance covered by the wave lambda 1 in time t. Hence, in medium 1, we write t is equal to, t is the periodic time, t is equal to lambda 1 upon v1. T is equal to lambda 1 upon v1. During the same time t, the distance covered by the wave is lambda 2 and velocity is v2. So t is lambda 2 upon v2. T is lambda 2 upon v2. From these two equations we write, lambda 1 upon v1 is equal to lambda 2 upon v2. Lambda 1 upon v1 is equal to lambda 2 upon v2, and therefore lambda 2 is, from this equation, lambda 2 is equal to lambda 1 v2 upon v1. Wavelength in second medium is equal to lambda 2 v2 upon v1. But we know this v2 upon v1 is equal to n1 upon n2. We have studied this. v2 upon v1 is equal to n1 upon n2, where n1 is absolute refractive index of medium 1, n2 is absolute refractive index of medium 2, and hence our equation 1 becomes lambda 2 is equal to lambda 1 n1 upon n2. Lambda 2 is equal to lambda 1 n1 upon n2. If medium 1 is vacuum, now we assume that medium 1 is vacuum, we consider lambda 1 is equal to lambda 0 for the vacuum. If medium 1 is vacuum, lambda 1 is equal to lambda 0, v1 is equal to c, that is the speed of light. Lambda 1 is equal to lambda 0, v1 is equal to c, and lambda 2 is equal to lambda. If we consider these notations, our equation 2 becomes lambda is equal to lambda 0, or our equation 1 becomes, substitute in equation 1, instead of 2 substitute in 1, lambda 2 is lambda. If medium 1 is vacuum, lambda 1 is lambda 0. Speed of light in first medium is c, that is the velocity of light, and suppose lambda 2 is lambda, our equation 1 becomes lambda is equal to lambda 0 into v2 as it is, lambda is equal to lambda 0 v2 upon c. Lambda 2 as lambda, lambda 1 substitute as lambda 0, v2 as it is, and in first medium velocity of light is c. We write this equation like this: lambda is equal to, see our next step, lambda is equal to lambda 0 divided by C upon V2. We write this like this: lambda is equal to lambda 0 C upon V2, one and the same, just rearrangement of the terms. So we get lambda is equal to lambda 0 upon n, lambda 0 upon n, lambda is equal to lambda 0 upon n, where n is, or we may write it as n2, is absolute refractive index of medium 2, absolute refractive index of medium 2. Lambda is equal to lambda 0 upon n. This wavelength is inversely proportional to refractive index. Wavelength is inversely proportional to refractive index here. That is the dependence of wavelength on refractive index. Lambda is equal to lambda 0 upon n. Wavelength is inversely proportional to refractive index. If nu1 is the frequency of light in medium 1 and nu2 is the frequency of light in medium 2, then nu1 is v1 upon lambda 1, v1 upon lambda 1, nu2 is v2 upon lambda 2 by the formula of the frequency. If we take the ratio of these two frequencies, we get, by taking the ratio of these two, we get nu1 upon nu2 is equal to v1 upon lambda 1 divided by v2 upon lambda 2. But in earlier equation we know v1 upon lambda 1 is equal to v2 upon lambda 2. Hence these two terms are equal, they get cancelled, and we get nu1 upon nu2 is equal to 1, or nu1 is equal to nu2. Nu1 is equal to nu2. It means frequency does not change, or it remains same if medium is changed. Frequency does not change, or it remains same if medium is changed. Now there are some conclusions. Our first conclusion is frequency does not change if medium is changed. If medium is changed. And our second conclusion is wavelength is inversely proportional to frequency of the medium. Also, velocity in the medium is inversely proportional to frequency. Velocity is inversely proportional to refractive index. Wavelength is also inversely proportional to refractive index of the medium. If refractive index is large, the wavelength of light in that medium is small, and vice versa. Similar is the case for the speed of light. Inverse relation is there. So this is about the dependence of wavelength on the refractive index of the medium. Now our next article is interference of the waves. This article is also very important. interference of the waves. Interference. Interference takes place when two or more waves overlap. Two or more waves overlap. The interference takes place, and this interaction of the waves, or this overlapping of the waves, two or more waves, is explained by using principle of superposition of waves. We can explain this overlapping of the waves, two or more waves, by the principle of superposition of waves. Principle of superposition of waves. One main thing is, for the interference, two or more waves must be there, and if these waves overlap, interference of waves takes place, and this interaction is explained by using the principle of superposition of waves. The principle is like this: when two or more waves overlap, two or more waves overlap, when two or more waves overlap, then each wave produces its own displacement, independent of other. The resultant displacement is vector sum that is addition, vector sum of displacement due to all waves. Displacement due to all waves. Again, see the principle. When two or more waves overlap, each wave produces its own displacement independent of the other, and the resultant displacement at that point is vector sum of displacement due to all waves. Now, due to this superposition of waves, there are some important points I am going to explain. This is the principle of superposition of waves. Two or more waves overlap. In the superposition of waves, first point is, if crest of one wave coincides with crest of other, crest of one wave coincides with crest of other, or trough of one wave coincides with trough of other wave. Crest, trough coincides. The waves are said to be in same phase. Waves are said to be in same phase, and resultant displacement is maximum. resultant displacement is maximum. Again here in the superposition of two or more waves, if crest of one wave coincides with trough of other, crest coincides with trough or vice versa, that is trough coincides with crest of other wave, the waves are said to be out of phase. Out of phase. The resultant displacement at that point is minimum. Resultant displacement is minimum. Same phase, crest, trough coincides. Out of phase, crest coincides with trough coincides with crest, resultant displacement is minimum. Now third point is, if amplitudes of waves are equal, our third point is here, if amplitudes of waves are equal, if amplitudes of waves are equal, that is A1 is equal to A2, that is equal to suppose A. If amplitudes are equal at the same phase point, the resultant amplitude is addition of these two, that is A plus A. Resultant amplitude is twice the amplitude of each wave. And at out of phase point, at the same phase point, resultant amplitude is 2A, same phase point. They add. Same phase means crest, trough, like this. Suppose this is first wave. And second wave having the same amplitude will be also here, like this. Amplitude adds each other, resultant amplitude is twice the amplitude. At out of phase point, suppose this is first wave, out of phase means crest of one coincides with trough of other, like this. Amplitudes are equal, they cancels each other, and at out of phase point, resultant amplitude will be 0. Then our next conclusion is, as intensity of wave is directly proportional to square of amplitude. Intensity of wave is directly proportional to square of amplitude. Here amplitude is twice the amplitude, so intensity will be more. At out of phase point, amplitude is 0, so intensity will be minimum or 0. It means at same phase points, intensity is maximum, and at out of phase point, intensity of the wave is minimum. What it means? There is change in the intensity of wave. At some points it is maximum, same phase point. At out of phase point, intensity is minimum. This change in intensity of wave is also called as modification in the intensity. It is called as modification in intensity of the wave and this modification in the intensity of wave is due to, or it is produced due to superposition of waves. Hence, our definition of interference is the modification in intensity of wave. The modification, that is the change in intensity. Modification in intensity of wave. Modification in intensity of wave produced due to superposition of two or more waves. Produced due to superposition of two or more waves. Waves is called as interference. It's called as interference of the waves. Modification means there is change in intensity. At the same phase point, intensity is maximum. At the out of phase point, intensity is minimum, and this modification in the intensity of wave produced due to the superposition of two or more waves is called as interference. If the waves are in same phase, the interference is said to be constructive interference, or it is a constructive. If the waves are out of phase, interference is said to be destructive. Interference is destructive interference. So these are the two types of interference. At the same phase points, we get the constructive interference. At the out of phase point, we get the destructive interference. Now we see the interference of waves on surface of water. Interference of water waves or interference on the surface of water, and we see how constructive and destructive interference is there on water waves. Now see here, vibrating, these are the 2 points S1 and S2 on the surface of water. Then electrically maintained tuning fork, 2 pins are connected to electrically maintained tuning forks, and they vibrate at point S1 and S2 simultaneously. It produces the waves, these 2 waves, electrically maintained tuning forks. 2 pins are connected to that prongs of tuning fork. If it vibrates, that pins moves up and down at points S1 and S2, and water waves are produced in the form of alternate crest and troughs. Water waves on the surface of water are produced in the form of alternate crest and trough. This continuous arc represents crest and dotted arc represents trough. Continuous arcs like this, crest, dotted arc represents trough, and in this way alternate crest and troughs are produced here. These waves have same amplitude and wavelength, and they are in phase with each other. same wavelength, same amplitude, and they are in phase. Now see here, at the points shown by these crosses, here continuous arcs meet each other, that is crest coincides with crest, or dotted arc coincides with dotted arc. What it means? Trough coincides with trough, again crest coincides with crest, trough coincides with trough. So along this line the waves are in same phase. Along the line shown by the crosses, crest coincide, continuous arc coincides, or dotted arc coincides, again continuous arcs, dotted arcs. So along this line the waves are in same phase. The interference is constructive interference. Along the two lines here, see here, this line and this line, the dots are shown like this. At the points marked by the dots, one crest and one trough coincide, one continuous arc and one dotted arc, one continuous arc and one dotted arc, one continuous, one dotted. It means here crest coincides with trough and vice versa. At the points shown by the dots, also here at the points shown by the dot, as crest coincides with trough or trough coincides with crest, the waves here are out of phase, and along this line we see the interference is destructive interference. So in this way alternate constructive and destructive interference is produced on the water waves. This interference phenomenon is observed in case of sound waves also and waves on surface of water. In case of light, scientist Young performed first experiment to study the interference of light. Okay, today we stop here. Thank you.